Let's now look at the heat and salinity balance, which is obviously critical for looking at dense water formation. This is the meridional section that we have seen in other forms before, showing the convection at polar latitudes with buoyancy loss creating sinking of water. In a broad sense, we will kind of create a simple model that says deep water sinks out beyond a certain depth, and then that water from the abyss is being returned to the surface with large-scale upwelling. And this is the wind-driven structure that we had seen with the doming in the low latitudes with the Ekman divergence and upwelling, of course dominated by the Pacific and Atlantic Oceans. The Indian Ocean has some upwelling in the western part of the tropical ocean, unlike the Atlantic and Pacific Oceans, which have it in the eastern part. If you remember from the trade winds, Indian Ocean of course has different circulation because of the monsoonal forcing, and we had the bowls being formed in the thermocline by the subtropical gyres. So these processes of buoyancy loss are critical for the deep water formation and thermohaline circulation. This is our old figure from chapter 5 showing us our annual mean and seasonal stream functions, meridional, zonal mean, meridional stream functions, showing the Hadley cell, which is the direct cell with weak polar cells, and the equivalent of that is of course the ocean upwelling and sinking. So you can think of this here as the Hadley cell. Then you have weak cells at higher latitudes as well. Okay. What happens with the air-sea fluxes and surface property distributions? We look at the zonal averages of the heat transfer into the ocean. Obviously, solar heat flux reaching the surface is very critical. You remember why there is a minimum on the equator in low latitudes and maximum is off the equator because of the deep convection, and it's not exactly on the equator, it's in the low latitudes. On the deep convection and deep clouds creating low energy loss from the top sigma t to the fourth, remember, and of course the radiation falls off at higher latitudes. You have sensible heat loss, which is very small. We will see the formulations for these sensible long wave we already know as sigma t to the fourth, and there is the latent heat loss. So you can see that latent heat loss turns out to be the major component in most places. At higher latitudes, of course, the air is pretty dry, so you don't evaporate as much, even though wind forcing can still rip off water molecules and cause evaporation. Sensible heat is basically the heat loss because of the temperature difference across the ocean atmosphere interface, and long wave is what the ocean surface emits because of its thermal radiation. Correct? You want the integration of the net heat flux, which is the sum of these terms as we had seen before when we did the mixed layer heat budget, to go to zero, because ocean takes all the heat and it moves it around and produces an equilibrium distribution of temperatures at some time scale, right? But each component is unfortunately estimated differently. Shortwave is either from radiometers on the surface or satellite data. Sensible heat fluxes are measured with winds and air temperatures, sea surface temperatures. Long wave latent heat is even more difficult. You need the difference of saturation, humidity at sea surface temperature, and low level air humidity, and so on and so forth. When people do that and add up these components, you end up with this gain in the ocean of something like 16 watts per meter squared, because it's not constrained to add up to 0. Okay, so when the constraints are added, there is a distribution that results like this, with some major latent heat loss in the subtropical gyres and little bit of a heat gain in the southern hemisphere, but not so in the northern hemisphere. The question really is, what is the uncertainty in these estimates? If there is an uncertainty of 10 watts per meter squared, for example, then the sign of this is suspect. It can be minus or plus, because it's of the order of few watts per meter squared. So estimating surface heat fluxes, hence the heat transport by the ocean, is not an easy task. We will look at some of the estimates provided by some of the people. So buoyancy we defined as minus g rho parcel minus rho environment divided by rho parcel. So buoyancy, typically when we want to see water sinking, we're going to go back to our concept of water parcel and look at its density with respect to the environment, and when it gets heavier it has to sink. Of course, the buoyancy depends on the reduced gravity or the relative buoyancy with respect to the background stratification of the environment, in which case it's the average density of the ocean, right? So we can write it in terms of sigma, because rho is written as rho ref plus sigma, you remember. So buoyancy in that case is minus g times sigma minus sigma naught divided by rho ref. Sigma naught is the background environmental sigma here. So sigma itself is written as sigma naught plus rho ref, thermal expansion coefficient, and salinity effect. Obviously we have said density is a non-linear function of temperature and salinity, so this is a linearized fit to the observed density or actual density. The heat budget of the ocean then should look like this: the temperature balance. This is of course our total derivative, substantial derivative, Lagrangian derivative, or whatever the way we talked about it in chapter 6, I think, where we derived the equations. Should be minus 1 over rho ref Cw, the heat capacity of the water, times dq dz, where q is the net surface heat flux. So just like we did d tau x dz and d tau y dz for momentum balance at the surface, we have heat flux and freshwater flux for temperature and salinity. Okay, this term obviously includes time variability of temperature plus the advection term like u dt dx, v dt dy, and w dt dz, right? And ds dt of course also includes time variability in the advection terms, equal to s times d epsilon dz, where epsilon is the freshwater flux at the surface, which is the net E minus P. Okay, fairly simple looking things, but obviously not as easy in the real world, because you remember our mixed layer processes. The specific heat of the ocean water is 4.18 10 to the 3. There is the latent heat of fusion, latent heat of evaporation, very critical, density of freshwater, viscosity, kinematic viscosity, and thermal diffusivity. We mentioned before that thermal diffusivity is 100 times larger than salinity diffusivity, but that's not going to be very critical here. This is the processes. These are the processes we mentioned in the context of mixed layer, but at high latitudes where deep waters actually form, obviously mixed layer is not very well defined. There may be a wind shear, but the temperature, salinity, and density will be well mixed to great depths. Okay, so mixed layer in that context is not very well defined, but nonetheless in most of the ocean, the processes of turbulent exchanges across the ocean atmosphere interface and the entrainment at the bottom of the mixed layer based on the turbulent kinetic energy available to lift the poor waters, the cold waters, poor waters, and mix them into the surface layer, and so on, determine the sea surface temperature distribution. Okay, we have seen the sea surface temperature distribution a few times, but now we are looking at the processes that determine this distribution. Okay, these are obviously going to be critical for buoyancy distribution and its variability in the ocean at the surface, because we are mostly interested in how density changes and buoyancy changes are being brought about at the surface.